to this edition of the Mathematics video series. In this episode, we will discuss base 10 and other bases. The number system we use is base 10. What this means is that every number we write has a position: ones place, tens place, hundreds place, thousands place, and so on. The one place is 10 to the 0 power. The tens place is 10 to the first power. The hundreds place is 10 to the second power, and the thousands place is 10 to the third power. Remember that 10 to the 0 power is 1, because any number to the 0 power is 1. It is so commonplace for us to think about the position of a number that we do this intuitively. In part because we buy groceries, get a paycheck, pay rent, and balance our checkbook. Thus, we use our positional notation every single day. We do not think to ourselves that 1,253 is really 1 times 10 to the third plus 2 times 10 to the second plus 5 times 10 to the first plus 3 times 10 to the 0. We actually just do it instinctively because we've practiced this over and over again. And we have it down. What makes this work is that every number that we write on a daily basis is in terms of 10. A dime, which is 10 cents, has 10 pennies, and a dollar, which is one whole amount, or 100 pennies. The decimal system does not flash through your head. However, what if we needed a system of yeses and nos so that we either went to work yes or did not go to work no? We went to school yes, we did not go to school no. Thus, our life would be reduced to a series of decisions and decision trees with a set of questions. Your alarm rings. Wake up, yes or no? If yes, then open your eyes. If no, hit the snooze. If you wake up and open your eyes, do you get out of bed, yes or no? If yes, sit up. If no, remain prone. If you hit the snooze and go back to sleep, when the alarm sounds again, do you wake up, yes or no? We follow this path too, although much more subconsciously. However, this decision-making pattern is not in base 10 because there are not 10 outcomes, but rather 2. Thus, we are in base 2. This is the basis for computer decision-making also. Although the process is laborious and requires literally millions of decisions as we type a report, open software, edit pictures, and do our computer homework assignment. Computers use millions of electronic switches in the form of transistors, which are either on or off, where true or on is yes and recorded as a 1, and false or no is recorded as a 0. Binary systems are also the basis for artificial intelligence, robotics, plane flight, and every other computer process in our life. However, artificial intelligence will become more and more embedded in our life within the next few decades, as these decision-making trees try to simulate the billions upon billions of decisions a brain makes every day in order to anticipate our needs. Google, Amazon, Apple, Boeing, and many manufacturing companies use artificial intelligence every day. Of course, your brain is still needed, so please keep following me. Every decision is either a yes or no, which means that we are now in base 2, or the binary number system. Recall that yes is a 1 and no is a 0. You might be asking why computers cannot use base 10. After all, wouldn't it give 10 choices rather than just yes or no? Well, actually, our digital computers are simply faster by using on and off switches, or 1 or 0, because it allows an electrical current to be present, which is 1, or current, and 0, which is no current. Although there are no base 10 options for this, it is just easier to be on and off, electrical current or no electrical current. Now we can count in base 2 in a similar way we can count in base 10. The ones place is simply 2 to the 0, rather than 10 to the 0. So in base 10, we have the numbers 0 to 9. However, in base 2, we only have the numbers 0 and 1. So in base 2, or binary numbers, we have 2 to the 0, which is 1, 2 to the first or 2, 2 to the second or 4, 2 to the third or 8, and 2 to the fourth or 16. If we want to write the number 25 in base 2, we ask ourselves, how many 16s go into 25? We know that 16 goes into 25 once, so we put a 1 in the 2 to the 4th power position. If we subtract 16 from 25, we get 9. Thus, we have 9 left. The next position is 2 to the 3rd, or 8. So we ask how many 8s are in the number we have left, which is 9. Well, 8 goes into 9 once, so we put 1 in the 8th position. We subtract 8 from 9 and we get 1. The next position is 2 to the 2nd power of 4. We ask how many 4s go into the 1? Well, 4 doesn't go into 1, so we put a 0 there. We still have just left a 1. The next position is 2 to the 1st power of 2. We ask how many 2s go into the number we have left, which is 1. Well, 2 does not go into 1, so we put a 0 in that position. Since we have a 1, we put that in the last place, or 2 to the 0 position. The resulting number is 11001. That means that 25 in base 10 is the same thing as 11001 in base 2, because 1 times 2 to the 4th plus 1 times 2 to the 3rd plus 1 times 2 to the 0 is 16 plus 8 plus 1, which is 25. Now we'll try one more. We will write 52 in base 2. Since 52 is a larger number, we can see that we need one more place because 2 to the 5th, or 32, goes into 52. So we add another column. Now we ask ourselves, how many 32s go into 52? We know that 32 goes into 52 one time, so we put a 1 in the 2 to the 5th position. We subtract 32 from 52 to get 20. Now we ask ourselves, how many 16s go into 20? We know that 16 goes into 20 one time, so we put 1 in the 2 to the 4th power position. If we subtract 16 from 20, we get 4. Thus we have 4 left. The next position is 2 to the 3rd, or 8, so we ask how many 8s are in the number 4. Well, 8 doesn't go into the number 4, so we put a 0 in the 8th position. We still have a 4 left. The next position is 2 to the 2nd power, or 4. We ask ourselves how many 4s go into the number we have left, which is 4. Well, 4 goes into 4 once, so we put a 1 there. We subtract 4 from 4 to get 0, so we have nothing left, and the last two positions are 0. Thus, the resulting number is 110100. That means that 52 in base 10 is the same thing as 110100 in base 2, because 1 times 2 to the 5th plus 1 times 2 to the 4th plus 1 times 2 to the 2nd is 32 plus 16 plus 4, 52. Now look at this chart to see how the numbers in base 10 compare to the numbers in base 2. So 0 is 0 as you might expect, and 1 is 1. But 2 is 1, 0 because you have 1 in the 2 to the 1st power position and 0 in the 2 to the 0 position. And 3 in base 10 is 1, 1 in base 2, which is really written 1, 1 sub 2 with a subscript of 2. So we have 1 times 2 to the 1st plus 1 times 2 to the 0, which is 3. Now, we have thought about binary or base 2. We want to extend this idea just a bit further. Computers have switches, or electrical yeses and nos. You might have heard of bits and bytes. Here's what that means. 8 bits is 1 byte, and a computer needs 8 bits or 1 byte to represent one alphanumeric character, or a single unit of information. So 2 characters require 16 bits or 2 bytes. You might have heard people talking about kilobytes, megabytes, or gigabytes. You might have even bought a computer where they referenced gigabytes of memory, or even terabytes. Here's what that means. 1024 bytes is equal to 1 kilobyte, and 1024 kilobytes is 1 megabyte, and 1024 megabytes is equal to 1 gigabyte, and 1024 gigabytes is 1 terabyte, and 1024 terabytes is equal to 1 petabyte. When someone is talking about the size of your picture or video file, you have a basis for comparison. How much memory is in your computer? How large is the size of the file? While we only talked about base 2 and base 10, just so that you know, there are other common bases that are frequently used, like base 8, which is the octal system, and base 16, which is hexadecimal. They follow a similar principle that we will not discuss here, but we will in a future episode. That's all for this edition of the Mathematics video series. This is Dr. Rachel Winston signing out.